Today we're going to talk about non-point source pollution. That was part of the outline that was designed by Thomas and Jessica. And for me, it's also an excuse to introduce spatial dimensions in our model of pollution. So you can see that I like modeling stuff in order to better understand what's going on. And here I will generalize the model we've seen last week to introduce space and more precisely how pollution diffuse across space, which is important for the design of environmental regulations. So my part of the lecture, you can see that as the box in the Thomas and Jessica textbook. So in their textbook, it's a very soft policy-oriented textbook in which you have a lot of story, case studies, and descriptions, and sometimes you have boxes with some kind of models. Here's the reverse. I will have a lot of modeling and some boxes with some case studies. It's maybe more Toulouse-style kind of lecture. So I will start this is the outline of today's session. I will start by a box of case studies to motivate the model. So I will start by introducing some, describing some contract-based policy, which has been launched by the US Environmental Protection Agency, which is about the water quality voluntary trading program. And you will see that in this case, the spatial dimension matters. That is, it will be a program for reducing pollution from agriculture, water pollution from agriculture, and farmers are compensated from their better practices. That is reduction of their emissions. And they are paid for that, but then you have to compute what are the damage impact of the reduction of emission, and the payment will depend on that, and that will be something that should be part of the regulation. Then I will introduce the model, so I will generalize the model we've seen last week to introduce diffusion of pollution across space, then provide some example of this model, some illustration about how you can apply this model to tackle several issues on environmental policy, like from SO2 emissions, air pollution, or water pollution in rivers, for instance. And then I will take the standard, microeconomics approach. That is, try to characterize the first best. What will be the optimal allocation of pollution in this framework? As you know, optimally, no pollution is often not optimal, and given the assumption I will take, it will not be optimal. So there will be some pollution, but more than under laissez-faire, so more than equilibrium. So I will also describe the laissez-faire outcome, what will happen if we don't regulate. So that's a motive for regulation, try to mitigate the inefficiency of the equilibrium with some regulation, get closer to the optimum. And in order to do that, we can use several instruments. So I will list those instruments. And so we rely on standard ones, emission caps or standards, emission fees, cap and trade, and one instrument has been proposed by Segerson to solve this non-point source pollution problem, which is the ambient tax, which is a tax rate which depends on ambient pollution. And then I will conclude by presenting some experiment on this ambient tax regulation, or several ambient tax regulations. So ambient tax is not the regulation that has been implemented, so as far as I know, that has been implemented in practices. But there has been some experiment on to try to figure out how, what kind of incentive this kind of regulation provides, and how subject will react to this regulation. Subject like a student in a lab, and that's all. That will be for the 2/3 of the session, and the last part we will talk about the problem I gave you last week. So feel free to interrupt me anytime. So let me talk about this program. The idea is to get paid for reducing emissions. So if you go in the Environmental Protection Agency website, you can find this report that has been published in 2006, which is, as I said, a voluntary program. A wind farmer can write contracts with municipality or companies that own mostly water treatment plants. That is, they want to reduce pollution at the source for getting better quality water where it is used. So these are, I'm not sure you can read it, but it is a short, I mean, if you go through the document, you get this description. So what is water quality trading? Water quality trading is a market-based approach to improve water quality being used in some watersheds. So you want to get better quality in the watersheds, not necessarily at the source of pollution, but at some places where it is used. So for instance, in a water treatment plant, for instance, or some other watershed, it could be also a natural reserve, like a biodiversity reserve, some marshes, and so on. So it is a tool that connects industrial and municipality facility, subject to wastewater permit requirement, with agricultural producers to economically achieve water quality improvement. These permit facilities are referred to as pond sources, so this is a pond source. And in this context, agricultural producers are referred to as non-pond sources. That's for the vocabulary. Through water quality trading, a pond source facing relative high cost to remove excess amount of substances, such as nitrogen and phosphorus from fertilizers, will compensate another party, either another pond source or a non-pond source, such as a farm of a ranch, so here, non-pond source, for less costly yet equivalent pollutant reduction. So you have like in the picture of what's happening. The farm accepts to reduce the use of those, let's say, fertilizer or pesticide to reduce the pollution of nitrogen or phosphorus, for instance, or pesticide. That has an impact on the watershed where it matters, at the buyer facility, and many municipality. And then this municipality compensate the farmer for his or her best practice, reduction of pollution. So that the idea, of course, the idea also is to improve efficiency. So instead of treating water, to reduce the cost of treating water, you reduce emission at the source instead of increasing the cost of treating this dirty water. So that will be the efficiency side. But in terms of fairness, you can also challenge the fairness properties of this principle, because obviously it violates the polluter pays principle. Okay. So you pay the polluter for reducing his or her emissions. Therefore, the polluter does not pay the impact of on her or his emission on the environment. So at the end will be the use of water, like you and me, but by the intermediary of the municipality or the company in charge of treating water and supplying water, for instance. So then you can have a look on the contract. So this is the kind of contract they can sign. So they call the pollution reduction credits. So this is the name of the facility generating credits. So the water treatment plant gets some credit from, paying for reducing pollution, and those credits can be then traded in the market. That's another part of the story, that you can generate some market for water quality in some sense. And then there will also be some farmer who signs a contract. But then the thing is, they have to compute some trade ratio. Okay, so they have to figure out. So they have to first to identify some management best practices, and then translate those practices in terms of reduction of emissions of pollution at the at the farm level, and then translate in terms of impact on water quality at the watershed, that is where water is pumped and treated for your own consumption. And this is done here, and this is where the policy is a bit difficult to compute. So you need a lot of information, and particularly some knowledge about hydrology, agronomy, chemical diffusion of pollution, and so on. This is what you have to complete it, and you need some expert to do that. And then you end up with some credit, and farmer can get paid from those credits. And also the idea also is you can exchange those credits on the market. That's also part of the regulation. You can see also there is some issue of monitoring, so some verification method and frequency of verification. Okay, so something which is part of this policy instrument course in one lecture by Jessica, I think. And that's the idea of organizing a market from that. So you start from some contract. So the contract is a little bit the kind of incentive-based regulation contract we have seen last week in this lecture. But you can also have contract with some intermediaries, some brokers that connect the farmers and the buyer facilities, buyers, sellers and buyers. And then you can also some aggregation of those brokers. So several farmers can deal with some brokers with the facility and so on. And then you can end up with a full market in which those credits are traded among you. So this is, implemented and used in the US, and you have some papers on, water quality trading in river basins, like along the rivers, and about the efficiency and welfare impact of those trading programs. Okay, so this is about the story, and now what about the model? So now, in order to introduce spatial issues into the model, I will rely on Montgomery's paper that has been published a long time ago. So you need to have agents, and some agents are polluters, some agents are victim of pollution, and some agents are both polluting and also victim of pollution. And you have to link those agents among them, and this will be done with those two sets. So for each agent, you need to know each victim of pollution. You need to know who are impacting their welfare. Who are the source of the pollution where the agent is located. Okay, let's think about the water treatment plant, I mean, or a river, like a watershed. Who are polluting this watershed? So that will be denoted as I, the set of agents, the source of pollution at I. And also for each polluter, if you if you know those sets, then you know all the connection among polluter and victims. But another way to write this problem is to talk about the receptor. For each source of pollution, you tell me who are getting the pollution emitted from this non-point source, then you get all the connection between victim and polluters. Now you need some assumption about preferences, and I will rely on the same assumptions like last week. So in that way, it's a generalization of last week's model. So I will work with emission, not abatement, but emissions. So it can be like emission of nitrogen, phosphorus, pesticide. It could be also air pollution, SO2, greenhouse gases. And there's a cost of reducing emission to a certain level of emission from the laissez-faire uncontrolled level of emissions. And this is, as before, decreasing in convex. There is some damage also, which is increasing in convex as last week. But what is new with the link between emissions and at the source and pollution at the receptor, okay, where the damage occurs. So that's why I will also distinguish between emission and pollution. Last week it was the same, here it's different. So for each level of emission, you get several levels of pollutions for each receptor. And the link will be made by this alpha ij parameter, which is called the transfer coefficient. Transfer coefficient. It tells you from each unit of emission at I how much this unit would lead in terms of pollutions. So the link between emission and pollution is made by this transfer coefficient. So it's the marginal impact of I's emission on pollution in J. So I, the first label is the source, and J is the receptor. So at the end, what matters is pollution concentration, where pollution matters, and it's just the sum of transfer coefficient times the level of emission. And this will be for each polluter that are affecting the pollution at J. So there is some linear transformation among the two variables, emission and pollution. I will provide a couple of examples. So this is linear, but when it comes to damages, this is convex, meaning the marginal impact of pollution concentration increases with pollution concentration or level of pollution. Could be in terms of concentration or absolute level. And you can have a general model in which some agent can be polluter only or victim only, in which case the damage are zero or the costs are zero. So it's a cost of abating, but expressed in terms of emissions.
Okay, yeah.
So remember that. So abatement is the difference between the laissez-faire emission and the level of emission, and the cost here will be something which is decreasing, convex, and this is the laissez-faire level of emission. This is equivalent. But I prefer to talk about emission because regulation will be on emissions, like emission cap or emission taxes. But you can do the same exercise with abatement instead of emissions. So formally, you can define those sets. So SI is a set of agents from which this transfer coefficient is strictly positive. and Ri also. That's just some notation. Actually, Jessica will post the slides on the website today. So here's an example, and for each example we will have some assumption, some specific assumption about transfer coefficients. So consider a river. Like this, and people are located along the river, and you can order agents or label agents along the river from upstream to downstream. And the water flows down that way. So in this case, agent 1, if agent 1 emits some pollution, then it affects agent 2, 3, and 4. If agent 3 emits pollution, it affects agent 4, but not agent 1 and 2. So then you can define the set of receptors of pollution as follows. So for each agent I, for instance, each agent I is receiving pollution emission from people located upstream. So for instance, for agent 3, the source of pollution at 3 is the set 1, 2. So S of 3 is 1, 2. And the receptor of pollution in 3 is, let's say, 4. So it could be also 3, depending if 3 is polluting himself or herself or not. So you think about 3 as a country or city. Could be that country 3 is also polluting himself, or it could be also that the city is clever enough to discharge wastewater, downstream the border of the city, for instance, the municipality. So that's about those sets, but then you have also to compute the transfer coefficient, and then it's related to the position, to those sets, but also potentially to the distance among agents, and also to other biological or physical issues or hydrological issues like the flow of water entering the river, absorption capacity, if some marsh or some tributaries along the river, then the transfer coefficient will be lower. So the transfer coefficient is for each unit of, let's say, pesticide emitted in 1, how much ends up in 2, in 3, in 4. So it's more likely that for each unit emitted in 1, there is less pollution, less of these emission ending up in 3 than in 2, for instance. Therefore, the transfer coefficient will be lower going downstream. Okay. Another issue is that you can have an agent at the end, if there is some lake, for instance, some coast for which pollution is important. Otherwise, it doesn't matter how much pollution you get at the end. Yes? I said that the impact will be positive within this set and equal to 0 outside this set. That means here, for instance, that alpha 1, 3 is positive, alpha 1, 2 is positive. No, sorry, alpha 2, 3 is positive, but alpha 4, 3 equals 0. Okay, so that is agent 1 and 2 are impacting agent 3, but agent 4 is not impacting agent 3. This is what I was meaning. So what I was meaning is that just by the sign of the transfer coefficient tells you about those sets. Who is impacting who. Okay. Another example. greenhouse gas emissions at the world level. Think about Asian as countries. Emissions are greenhouse gas emissions. But well, the only big limit in this model that is static, whereas greenhouse gas is a stock pollution, and what matters is also the dynamic of this pollution. But abstract from that, you can represent this model. You can also represent climate change and greenhouse gas emission in this model. In this case, every country is impacting every other country. Okay. So that's why the source of pollution that ends up in the of CO2 concentration, let's say, that end up in Sweden, is the world. Sweden is impacted as much by CO2 emission in Japan than in Norway, for instance. And that's also why the transfer coefficients are equal. So it's a model of global pollution with a symmetric pollution. Each country is, impacting the other country the same way for each ton of CO2 emission, let's say. Damages are different, of course, but in terms of CO2 concentration, we are all in the same boat. You can so the transfer coefficient is the same for the same greenhouse gas component in terms of CO2 equivalent, but you know that some greenhouse gas are more the same unit of same ton of some greenhouse gas have more impact on climate than CO2. For instance, methane impacts to 23 more time than CO2 climate. But if you measure in terms of CO2 equivalent, you get the same transfer coefficient. And then you can emission EI will be the greenhouse gas emission, and PGI will be the greenhouse gas concentration in the atmosphere within the country. Another air pollution problem, international transboundary pollution problem, is SO2 and NOx emissions that are causing acidification, acid rain that are causing acidification of lake and forest, and also buildings, so damage on building, and also loss of biodiversity. And also SO2 emissions also are causing some health problems, but mostly locally, whereas for acidification it's mostly globally. The idea that those pollution are going to atmosphere and going down through the rain, often far away, depending on the wind, in other countries. So then in this case, it's not completely symmetric, and the diffusion is not uniform. So it's partly symmetric because each country who is emitting is at the same time victim and also polluter, but the rate of emission differ, and more importantly, the pollution or the emission are not diffusing uniformly, let's say in Europe, for instance. So then the transfer coefficient is related to the transportation of SO2 or NOx emission among countries. And you can have some estimate of those transfer coefficients. So there's a paper by Meller and Deziu which estimates as the amount who provide some estimate of those transfer coefficients, though they calculated from each ton of SO2 emission emitted in one country, how much ends up in the same country or another country. So you know that, for instance, for each unit of the emission from Belgium, from the emission of Belgium, 20% end up in Belgium, 30% in Germany, and 9% in France, and so on. So that will give some measure of those transfer coefficients, for instance. And the pollution will be sulfur concentration. So you link SO2 emission with sulfur concentration, let's say in water, for instance. And that impact the acidification of lakes and forests, for instance. So Belgium is emitting SO2 and NOx because Belgium, for instance, is using coal for producing electricity. So those SO2 and NOx emissions are going to atmosphere, and then some are moving, some are staying, and then the sulfur is going down with rain, and are polluting lakes and forests. But some of the sulfur is moving in other countries. So then those statistics tell you that for each ton of SO2 emission, 20% will end up within the country, and 30% will go in Germany, and then 9% in France. So it's related to the distance, but also the weather, the climate, the wind, and so on. So, for instance, so Sweden is affected by mostly by emission in Poland, and Canada by emission in the US, for instance. So we will see tomorrow that I will talk a little bit about that. There's some European agreement which is dealing with this kind of SO2 and NOx emission. Okay, what about the laissez-faire? So if there is no regulation, what will happen? How much each agent will be emitting? How much is victim of pollution will suffer from pollution? So in general, if you pick one agent, and assuming that this agent is a polluter and a victim at the same time, like think about a country like Belgium. Belgium decides how much to emit in terms of SO2 emission, and is also victim of sulfur concentration, and that causes some damage. So level of emission will minimize the overall social cost of emission for agent I, taking into account the transfer coefficient. So far in the model, we had one here and here. We also, last week, it was a model in which we have only victim or only polluter. So if there's only a polluter, forget about this term. If the guy is a victim, forget about this term. Does not show anything, just suffer from pollution. But in general, it will solve this problem. And then when you compute the first condition, you get this expression, which, so what is the interpretation of this first order condition? You equalize what? This is a question. Marginal abatement cost on this side. And this is marginal damage. Take into account this transfer coefficient. And here you have the only transfer coefficient from I to I. So the problem is that agent I cares only about the damage of his own emission, his own damage on his own emission, or like Belgium cares about the impact of his SO2 emission within its territory only. So that's why the agent will choose the level of emission that equalizes its marginal abatement cost, so the marginal damage in I, for I only. So this is d prime I. And taking account the transfer coefficient. So the idea here is that you have to take into account that for each ton of SO2 emission, only 20% will end up in Belgium. So that is the marginal cost of reducing emission by 1 ton of SO2, and this is a marginal benefit for Belgium. The benefit will be also that only a fraction it will translate into only a fraction of reduction of pollution concentration, of sulfur concentration in Belgium. And this fraction is 20% here. So you have 0.2 here, for instance. And the marginal benefit is the marginal damage. The marginal benefits of reducing pollution concentration of Y unit is the marginal damage. So then you equalize. If the marginal abatement is higher than this marginal damage times the transfer coefficient, that means that abatement is more costly than the benefit, and therefore it's not optimal. In the reverse, if the marginal damage is higher than abatement, that is not. You should abate more because abating is cheaper than the benefit you get. Okay, so then you can compute the laissez-faire. You can compute the pollution concentration, and you know that if there is no damage here, you think about a firm with which is not impacted by its own pollution. This will be equal to 0, and then therefore a firm will choose its costless emission level. That is, the firm will not abate any emissions. Now, what about the first best? What should be the first best level of emissions? Here, first best is defined by a vector of emissions for each agent, which maximizes total welfare, or sorry, minimize total social cost due to emissions. So you sum up cost plus damages, cost plus damage for each country. So costs plus damages with the transfer coefficient in the pollution concentration. And then if you take the first order condition, this is what you get. So what's the difference here compared to the laissez-faire? This is this term. So you equalize the marginal abatement cost of each polluter to the sum of the marginal cost of each victim of this pollution times the transfer coefficient. So the idea is that every time you reduce emission by 1 unit, you increase the benefit of all the victims. That is, you reduce the marginal damage for all victims by alpha ij units. So here you have something which is close to the Lindahl condition for public goods. The Lindahl condition, you told you that when you provide public good, you should equalize marginal cost of providing this public good to the sum of marginal utility due to the provision of the public good. So here you have the sum of marginal utility here, but you have also the transfer coefficient. So if you think about greenhouse gas on which those transfer coefficients are equal, you have just the sum of the marginal damage. And the inefficiency comes to the fact that each agent cares only about its own damage and not the damage of others. Okay. And that's why, in general, you get more emission on the laissez-faire compared to the first best. Okay? Clear? So these are some application of this model for some specific cases. So if you have only one polluter and one firm emitting and several victims, then you get this first order condition for efficiency. That is the marginal benefit abatement for the firm equal to the sum of marginal damage for all the victims. You can have also a model with N-1 polluters and only one victim. So several firms that are impacting some population located around population of citizens located around the firm, like a city. Then you get an interesting feature of this case is that you can then get this condition. So when you compute, so going back to the general model, you will get the same first order condition, but with only one victim, so forget about the sum, you get the marginal damage times the transfer coefficient for efficiency. So, and then, so you get, for instance, let's do for two firms, you get minus C prime 1, E1 equal to alpha. So let's call two firms, 1 and 2, are polluting city agent 3. So this is the pollution. So therefore, alpha 1, 3 are positive, alpha 2, 3 also are positive. So this will be the first order condition for efficiency for firm 1, and this will be and why I'm doing that? Because then you can maybe recognize some general principle in environmental policy, which is the equimarginal principle. What does this equimarginal principle tell you? So forget about the transfer coefficient. What do you get? Equalization of marginal abatement cost. So efficiency requires that you should equalize marginal abatement cost across firms. And that's why you should have a unit tax in general for, like, say, carbon CO2 emissions. So it's a very general principle which can have many implications. You know, when you talk about environmental policy, I mean, politicians talk about environmental policy and can start to say, okay, we will launch a new tax on this pollutant, but you know, maybe farmers should be exempted, maybe, you know, fishermen should be exempted because it's very costly for them to run. Then you know that this will violate this equimarginal principle. If you don't, you should have the same tax for, let's say, CO2 emission for all, you know, emitters to get efficiency. As long as you reduce tax for some polluters, that violates this equimarginal principle, and you don't get efficiency. So the implication of this equimarginal principle is to have the same tax, the same tax for all polluters, expressed in terms of, you know, in terms of pollution. But now the problem is that you have also pollution diffusion that matters. So the equimarginal principle should be the same for pollution concentration, that is, the abatement cost of reducing emission concentration should be the same for all source of emission, source of pollution, so all farmer or, you know, firms. But that means different level of different abatement cost for emissions. Okay, so that's the point, that this equimarginal principle still hold when you talk about abating in terms of pollution concentration at the receptor of pollution. Right? But if you want to figure out what does it imply in terms of emission, you have a modified equimarginal principle. Okay, that is that this will be the level of abating emission, and this will be the cost of abating emission for agent I, and this will be the cost of, when you divide it by the transfer coefficient, this is the cost of abating pollution from source I in N, suffered by agent N. Okay. So you should equalize abatement cost per unit of pollution. That's okay. And that can be done, for instance, by taxing pollution at N. But then you should trace back for each unit of pollution at N, how much is emitted by each source of pollution, by agent I and agent J and so on. Okay. That will be the difficult part. Okay? Have you finished? Oh. I'll let you write down. Divided by the transfer coefficient. Don't forget to divide by the transfer coefficient. That's important. Forget about the... so international river problem is the same problem as before. Okay. So I stop now for the break, and after the break we talk about environmental policies.